weeks are pretty brutal. And we're exhausting, right? I think we need a Monday off every week. I'm going to promote that idea. Whew. All right, so let's just settle in. Take a second for yourself. Do this for your mind. Just settling in, noticing your body. Whatever sensations actually just rise up in your awareness. Can you see how your awareness is flickering, kind of jarging about? Hard to grasp any particular sensation. Let's try to bring that flickering awareness to a little bit of focus. Notice what our faces feel like. With your eyes closed, face actually feel like? Where's the edge of your face? Purely based on your experience. Spotlights in our mind. All right, friends. It's a whole new world for me. I finally got some decent N95s. Got these. Took weeks to get here. This feels good. My ears aren't being like shanked off. But that week I had for the first couple, or that mask I had for the first couple of weeks. Pretty brutal. Those were Department of Corrections masks. My wife's a lawyer, and so she gets to go visit her clients in jail, and DOC makes bad masks, I'll tell you that. Anything you would like to talk about? We've got some homework. I don't know when it's due. When is that homework due? Friday. Friday?
Yeah.
That sounds right. That sounds like some day I would make things due. What's that?
Due Monday.
Was it Monday?
It's the 4th and 5th.
Yeah, and it could be that. That's okay. We can make it that if that sounds better to everybody. No, was that like a surprise to you that it was Friday?
Yeah, but I have a week, so I'm not worried.
It's cool, but yeah, others might be.
I would have been surprised if it was Wednesday.
Yeah.
No, that's too much pressure on me too. Then I got to get shit done and back to you guys faster. Would anyone like the homework to be due Monday? Yes, Mike, I'm hearing a yes from Michael. That's cool. we're a small group, we can negotiate things. I've got a feeling you're not gonna just start it on Sunday, so I trust you to, right, Mike? No, I know you're up and ahead, you're doing all the reading. So, on that homework, Kayla, you look like you might have had a question?
I didn't get to work through it a whole lot. I don't
Okay.
think I have a question though. Cause it looked like a lot of it was like doing similar exercises to what we've done in class thus far. So maybe I'll come back with more questions on Wednesday.
Okay, that's cool, I appreciate that. You're thinking like 138 maybe, or?
Yeah. But also like 9, like show that it exists kind of thing.
Okay,
Like,
gotcha.
Show that there's this, like if A is a subgroup of B, then sup A is less than sup B. But also B must be an upper bound for A.
Yes. Yeah. I mean, if you want to take a little more time to think on that, I'd be happy. We can spend all day Wednesday, you know, as far as I'm concerned, talking about homework, so.
Cool.
Works for me. Anybody else? We good? Okay, cool. We got enough to do, certainly enough to do today. Since the homework's due Monday though, it would be a week from Monday. It would be great to have all questions like Wednesday or office hours, you know, Thursday for our Tuesday, Friday. That would be great. I'm not a fan of last day questions. Okay, cool. Let me grab one of my good pens. So, let's warm up. Been a while. It's quite a while when we have these 2-day-a-week classes. If I write this on the board, and I were to ask you, what is that? What would you answer? So what does it mean to say something is complete? We know the axiom of completeness says something. What is that something? Yeah, Noah. No, you shook your head no, so I'm sorry, I shouldn't have.
No, I can, any group of numbers bounded above have a least upper bound.
Any group of reals, let's be
Reals.
super precise, yes. So any subset B of R with an upper bound has a least upper bound. And we could do an infimum version of this. We could do, if there was if it was bounded below, there could be a greatest lower bound. Same thing, the symmetry of the real line, you could flip it left to right, looks pretty much the same, except for, you know, coordinates and stuff, but it looks the same. And then we said, well, what if we just restrict our attention? So this is R, right? This is when you've got everybody. What about the rationals? If we just restrict, Kayla, you're looking like, give me a thumbs down. Yeah, do you have an example?
Our ancient Grecian number line, sad face.
Yes.
Yeah, so like, let's say that we're looking at between 0 and √2.
What a good example.
Oh, thank
Indeed.
you.
Yeah.
Because the approximation of √2 will forever be like, you can't rationalize it essentially, and so therefore, like only looking at the rationals requires, in order that it be complete, that we have the irrationals.
Yeah, absolutely. The least upper bound of this does not exist unless I'm allowed to look at square root of 2. Right? So for this thing here, if we're looking for the soup in just Q, then you're gonna fail. That's not gonna happen. So we need to have the irrationals as well to be able to make this claim up here. But this is a pretty weird ass subset. We'll learn more and more. Even today, we're gonna learn more about it. What about if I ask this question with just the integers? What if we restrict our attention to the integers? So in other words, any subset, let's see if we can phrase this. We're going to ask, is this a valid claim? Any subset, so question, subset S of Z with a least upper bound has, oh, sorry, with an upper bound, has a least upper bound in Z. So kind of this problem, but a lot less stuff. Way more spread out. And the rationals are crazy. What do we think? Is that a true statement? You can see in one nod. Take a little private vote, write on a sheet, yay or nay. I'm with this. You can try to convince yourself, right? So how many yays that this is true? How many yays we got? 1, 2, 3. And then nays. And we have 2 abstains. We have 2 abstentions? Okay. So let me hear your nay, Michael.
I just feel like when we talk about like going from the reals to the rationals, you have like no holes ever to one set that has like holes in it. So I feel like when you have a set that's mostly just like dots spread out from each other, I don't know.
Well, let's draw like one of those kind of sets, right? So bounded above, let's say, gosh, and they're gonna look like this, right? Oh gosh, I could skip one in there if I wanted, but they're all gonna have this flavor. And maybe it could even go that way forever. That's cool, because we're just like, does it stop somewhere? So with this one, let's say 17. I don't know why. Boy, I never worked with that part of the line. Why not? Does this have a least upper bound? It does. What would it take to not have a least upper bound? Can you think of an example of a set of points in Z, stops like this, doesn't have a least upper bound? It's hard to, right? Like, it's impossible to. And so let's go back to, you were like thinking about Q and how messed up Q was. The messed upness of Q is because of how close things are, how tangled up the whole thing is. Here we're pretty cool. So this is actually, if you voted yay, that I think that's the way to vote on this, but Michael helped us gain insight with his nay, so so wrong answers are valuable, quite valuable. So this is actually a true statement. Absolutely. And we'll probably see something today that might help us. It's certainly going to be very related to this, the Archimedean, some Archimedean property, I forget what it's called. If you read 1.3, you know what I'm talking about, right? It's in there somewhere. Cool. So I just wanted to warm up thinking about completeness and where it might and might not manifest. Here's just a real quick question. What about in the plane? So we know that R has this completeness property. Can I formulate something like that in the plane? We've got reals. I'm going to tell you the answer is no, but you tell me why. What's the problem, Kalish?
Like if your function is root x, like there exists, like on the plane, like there are negative x values, but there's no output for root x in the negatives because those would be non-real.
Okay, cool. I think, so that everything you said there is true. I think maybe I haven't asked this question clearly enough because I think you're headed down a different route.
Okay.
So, so this is all about subsets of the reals here, right? subsets of the plane. Now I'm just talking about collections of points in the plane. So here's one. What does it mean to be, can we talk about bounded above? Michael?
You guys think all the stuff in complex, you have to use their distance from something, so it's from the origin.
It gets more complicated.
Yeah.
Yeah, which of these points is greater than this one? What does it mean to be greater than in the plane? Right, so over here, let's talk about this. We have a ordering. Here we have a well-ordered set. And that means any two elements, R and S, can be compared with a less than or equal. No matter what two real numbers you pick, you can compare them with this comparator. Over here, good luck trying to decide, let's do it like this. Which one's greater? Michael was suggesting maybe we could look at like distances from the origin. And that's something we could do. Just a weird little fact, you can put an ordering on the plane, but it's called dictionary order. So there's a couple of ways to put an ordering on the plane, and these are called topologies, actually. But you could use this thing called dictionary order. You could say, if I have 2 points, R, S, you don't need to write this down, and R prime, S prime. I didn't even know I was going to talk about this. What you do is you first compare, it's like ordering 2 words. So if you have like apple and above, how do you order these? Well, you look at the first character, and if those are the same, then you move to the next one. So here you could do something like this, if R is greater than or equal to R prime, or greater than, or R is equal to R prime, and then S is also greater than or equal to S prime. So it's kind of like this. You got this point here. This point would be greater than it. So with this point over here, and then points down here and to the left would be less than it. I kind of wish I hadn't just started talking about this. So sorry. Let me get myself back on the train, and let's talk about stuff we need to talk about. So if you read 1-3, let's just do a little karma-free test for you. What is the nested interval property? And just for these things, what is the basic idea? This is going to be a consequence of completeness. We talk about a bunch of consequences of completeness. Yeah, how well can you write that thing down? Michael, you're going to like today because we're going to build lots of stuff too. Here comes the building that I promised. Oh, yeah.
So
Go
is
for
it
it.
for any AN, which are subsets of the reals that are non-empty and bounded? Is that another thing?
Okay, so you said AN.
Like the big AN,
Oh, gotcha. Okay, cool. So capital A sub n.
such that AN plus 1 is contained in AN, going blah, blah, blah.
Like that. Okay, so if.
And
yeah.
the left endpoints, little a of n, the set of left endpoints have a supremum, was that?
I think you're thinking of the proof. I think, so the assumptions, can anybody help? So this is getting there, but there's something above this. What is A sub n? We know exactly what these things look like. They're not just arbitrary subsets. What are they?
A set of real numbers where x is between a sub n and b sub n.
Oh, nice. Okay, cool. So, yeah, inclusive, right? And we could just use this notation for closed interval. They are closed intervals. So, so we can have this, and if this happens, and this is for all natural numbers, this is also for all natural numbers. Let's make a picture. So a sub 1 is a set that looks like this. A sub 2 is a set that is inside this. Now it could share some commonalities. For example, the right endpoints could be lined up, but it's getting a little bit smaller. So we've got like a sub 2, b sub 2, and we're looking at these dudes, like so. And then let's just do one more. A sub 3 could share the left endpoint here, but it shrinks a little on the right. The key thing is they never grow as we move down the chain. So we've got nested intervals. It's right there in the title, right? We've got intervals and they are nested in, within each other, like an infinite Russian doll. Right? Just little dolls within dolls. So if this happens, then what is the big bang? Diana, do you know? Top of your head, what's the payoff if I have this? No, that's cool. That's cool. Anna, you know on this one?
No, how to refresh my memory.
That's okay. Okay, cool. Noah?
Non-empty. The intersection of all of them is non-empty.
Beautiful. This is lovely. Then there's something inside of all of them. We have this infinite intersection, and that is non-empty. There's a few ways to prove this. I really like the proof in our book because it's one of the reasons I got into analysis, just building stuff. Try building something in abstract algebra. What, no, it's just like, no, I'm gonna go out and fly my kite and watch how the kites interact in the sky. To me, that's about as close as I can get to understanding that. But here, we're gonna get in there, prove this thing. We're gonna build that shit that's inside the middle there. So proof. We will construct, which will be a big theme in this class, we will construct an X that's inside of this intersection. Now I'm flipping around with different indices. I hope this isn't troubling anyone. Sometimes I use K's, sometimes I use N's. It doesn't matter. They're just placeholders. It's like the variable of integration. All right, so let's think about some candidate. Let's go through the book proof, but we could do the book proof in a backwards way that I'll ask you about. But first we need to have a candidate for X. And let's think about how these sets are moving. The B's are always going to be above all of the A's. Why is that? Why does any particular B why does any particular B have to be to the right of all the A's? No, Michael, yeah.
Because A1 contains all of them and B1 is the supremum of it?
Okay, so how about this? Okay, I like that. So we definitely seems like B1 is greater than or equal to all the A sub K's. Because otherwise, if there's some A sub K out to the right, I don't think they're nested. So the nesting means that if you take this B1, somewhere down the line, there's not going to be an A sub, 173 popped outside there. Because that would mean that there's a B to the right of it. And that interval would not be inside here. So this is absolutely true. 100%. So B1 is an upper bound on all the A's. So let's think of the set of all the left endpoints. So this is B, the collection. The collection is the set of all left endpoints. That K is assumed to run from 1 to infinity. So they're all in there. This is just a bunch of points in the plane now. B1 is an upper bound on this set. In fact, any of the B's would work. Let's write that up and see if you can convince yourself of that. So in fact, any B sub K, or A B sub N is an upper bound on this set. Take a minute and convince yourself of that. Even though the B's seem to kind of slip to the left of B sub 1, potentially. Why can't there be some B sub N that's to the left of an A? What if there was? So you've got this, you're like, oh, I found one. I found one. B sub 1003 has to be to the left of some A. And it turns out that it was A17 that it's the left of. To the left of. Why couldn't that happen? Because they're freaking nested.
Okay.
Yeah. So the nesting gives us a lot of power here. So this can't happen because, wait, that's the right endpoint of something. So that would mean that A sub 1003 is to the left of A sub 17. And that's not going to be, this is going to be garbage right here. Because that doesn't make sense for set, but I just mean to the left of. Okay, cool. So we have this. We have a bunch of upper bounds. Thus, what exists for this set? What can we say exists for the set of the collection of all left endpoints if they're bounded above? Don't make me dance anymore. You're probably wishing it would stop anyway. So to make it stop, why? What exists? Oh, it's going to get worse. The set is bounded above by some number, thus fill in the blank. Ah, thank you. Good. Oh, thank God. Everyone can thank you for not having to see this. So the supremum of this set exists. Sup of A sub K exists. There's a least upper bound on that set. That is completeness. If I'm bounded above, I've got a least upper bound. Yay. Okay, so how about, so think about what's happening here. We're saying there's some sup. What if I called it X, and it's the least upper bound on all these left endpoints? You can kind of think of them as getting closer and closer to that X in some way, but never going past it. So let X equal the sup of this set, and this is our candidate for what's inside there. So the next step is, why is X less than or equal to any particular B? Why is that the case? And it's all right there.
Because it's,
Oh, yeah.
well, we've stated that it's nested, so if AK is approaching X, which is the supremum of the set, but AK must be less than BK, then X must be less than BK.
It's in there. It's
Okay.
in there. What is the, let's talk, you and me. So what was the definition of X? It was the
The soup of AK.
It was the soup of A sub K, right? And so it's the least upper bound on AK. What are some other bounds on that set, A sub K?
B.
The B's.
Yeah.
Yeah, so all of the B's are upper bounds.
Oh.
So X being the least upper bound must be less than or equal to all of them. It's so almost obvious in a way that the words just feel like they're tangling around. So this, because X is the least upper bound. Sometimes it helps to say love, our least upper bound on A sub K. And B sub N is an upper bound on this set as well. That means, by definition of least upper bound, this must be the case. So this is by definition of least upper bound. What about this? Also, we know for any K. Why is that?
Because X is the supremum.
Because X is the freaking soup of that set. So it's bigger than or equal to all of them. It's an upper bound on this set. Because X is an upper bound on that set. So check out what we've got. We've got, now, put these two together. Thus, X is bigger than or equal to any A sub K. It's less than or equal to the companion endpoint. And this is for all K. And that puts X in every interval. That's literally the definition of each one of these intervals. So, let's finish this up right here. Thus, X is an element of this set for all K, and that puts X in the intersection of all those sets. And so this is non-empty. And that's our proof. But we built it. We built it with supremums. A supremum, just a single supremum. And using the properties of what it means to be a supremum. This follows. So, does this property, let's take a look at this nested interval property. Here I've got a closed and bounded interval. Right, that is closed in the way that you normally think of it. We're going to get really into what closed means in here, but you would probably call that just naturally a closed interval. You'd be right. It is a bounded interval because it doesn't go off to infinity in either direction. Is this true with open intervals? So if we relax the hypotheses, is this true with open intervals? And here, let me just, something like this. am I guaranteed that this is always non-empty? You might have a homework problem that relates to this from 1-3. Quite possibly, I think there is. Actually. What are you thinking, Noah?
Well, put A n equal to B n, then there's nothing in it.
Oh, so when we use this notation, you basically, you have to have, you wouldn't write this.
Yeah.
You literally do have to have some kind of space in there, so. I like the way you're thinking though. You're thinking in the right direction. Let me just start drawing some pictures. So these are all left, this left endpoint here is 0 for all of these. What's inside all of those, if I keep on going? What is inside? I gotta run to the restroom. Perfect time. What is that intersection and why? Yeah, what you think, Michael?
I said the intersection is empty because for any element x that's in some interval 0 to 1 through n, using the Archimedean principle, there exists some m natural number such that 1 over m is less than x.
I like it. I was going to say the same thing myself. At least the Archimedean principle part, right? So this is actually empty. There's nothing in here. And this is, remember that I said there's this like archetype example, and we did it like day 1, of these nested sets, and they were slipping to infinity, I think, our sets. They were slipping away to infinity. But they had an empty intersection. There was nothing in all of them. This is the counter, this is kind of the reciprocal of that, literally. So let's just formalize Michael's excellent proof. So, proof that it is empty. This is bad. It refers to this, sorry, not the best. Assume it's not. Assume there is some, so this isn't terribly constructive. In fact, it's not constructive at all, but there is something inside of all of these. The Archimedean Principle, Part 2. I don't know if you remember, hopefully you read that, 1-3. Archimedean Principle, but can you imagine, I don't know, is that probably EAN. Can you imagine having done something like thousands of years ago and having people people still talking about it today. This is ridiculous. A lot of good work was done a long time ago. We've been kind of riding along, cutting and pasting since then. So by the Archimedean Principle, part 2, at least as it's stated in our book, given any positive real x, which this must be positive, right? I mean, it's certainly greater than 0. There exists an m, it's a natural number, such that 1 over m lies to the left of x. In other words, no matter how close you get to 0, this isn't terribly impressive if x is a large number. When x is 1,000, duh. But we're talking about x's that are really close to 0, so positive lying to the right. There's always going to be some 1 over m to the left of that thing. And herein lies basically the crux of why this must be empty. Because I've said there's some x in all of these. It totally contradicts this principle, which we're not going to prove. You can read the proof in the book if you'd like. Yeah, so check this out. This essentially means, if we let's just use what I got here. Thus, x can't be in this interval. It can't be in the little open interval created right there. Or for any with m bigger than that. And this contradicts the assumption that x is in all of them. So, good work, Michael. Absolutely, that's empty. We need closedness. Here's why we need boundedness. Let's just talk about that real quick. And it's not obvious why I'm making a big deal out of closedness and boundedness, but they're two really awesome properties that create another property that we will deal with this semester called compactness. But also the intervals must be bounded. And here's why. We don't want this to happen. You could even have them closed if you want. But I don't want something like this. Here's 1 to infinity. And then the next one is 2 to infinity. And see how those are nested, but there's nothing in the intersection. Could you tell me there's something in the intersection? You say, wait a minute. There is some y way out here that's in the intersection. No, there isn't. Because there's always some integer to the right of I, of any y you pick. So eventually, there will be somebody to the right of you, and we'll call that k. So y would not be an element of this k infinity, eventually. And that's actually the Archimedean Principle part 1 in our book. That given any number, there's a whole number to its right, which seems really obvious, but it's actually not an axiom, it's a principle. It's like a theorem you can prove. So I think you can read the proof in the book. It's weird. It's weird to go back to something so primal and think about how to prove it. All righty. Any questions about any of that?
So could you say that 1 over infinity is equal to 0, since you could always choose a number that makes it as arbitrarily close to 0 as you want?
I wouldn't say that exactly, but what I would say, Noah, is that I would say a couple of things. And I would also say this. But I wouldn't say exactly what you said.
Okay.
Okay? Yeah. Just a little more careful. Because once I got this, I just opened a whole shitload of worms.
Yeah, that's interesting.
Right? So just like crazy, things kind of crumble around us when we allow certain things to happen. I mean, it's always fun to watch them crumble. Always fun. Any other questions? That's a great question. But that,
So-
your idea there, that's exactly the idea behind that proof.
But when you do like L'Hopital's, like in the later parts of calculus, like Calc 2 and Calc 3, like you have to make those assumptions. So then what are we making those assumptions based off of?
So wait, okay, let's back up. This sounds like a big question. So you're thinking about L'Hopital's rule.
Right, yeah, so like you can use L'Hopital's for 1 over infinity or 1 over 0, and then later you can use like 0 times infinity or like 1 to the infinity. Do you know what I'm saying?
I do know exactly what you're saying, but
So then-
L'Hopital's only, it doesn't apply to 1 over infinity.
Okay.
It's only these indeterminate forms like this, Kayla.
Oh, okay. So,
But it's cool. I love that you're like thinking back. Like that's awesome. No, it's great.
okay.
Yeah. We must disabuse you of that notion, though, for sure.
It might have been a couple years since I took calculus.
It could have been.
Yeah.
It could have been. I think I
Yeah.
remember at least part 3. That seems like a lifetime ago. Any other thoughts, questions, comments? Okay, so the next consequence is the density of Q and R. Density Q and R. So this is a fundamental piece of the puzzle of how does Q live inside of the real line? What does it look like? What is happening? We're never going to know what it looks like, but we can gain these senses of what it's like, you know? It's like reaching into a dark box and just kind of feeling and getting, oh, it's fuzzy. Oh yeah, it's nice and fuzzy, but I don't know what it looks like. This is kind of fuzziness in some ways. So the official thing is this, given any 2 real numbers where one lives to the left of the other, no matter what those 2 numbers are, there is a rational number between them. This is probably something you've taken for granted, but maybe never really thought about in detail. So given any 2 real numbers, there exists a Q in Q that lives between them. Let's take this, let's actually make this word an official definition for us. In general, a set S is dense in a set R. And both these are subsets of the real line. And that R is, I shouldn't have stuck with R, but it's a less fancy R. It's just subset R. It is like. So this is the reals. They're both subsets of the reals. If given any 2 elements in the bigger set, there exists an element from the thing that is dense in the other set, so in S, that lives between those 2. So that's density in general. That's what we mean here. But this is good enough for right now. The proof is awesome and tricky at the same time. We will build Q. That's the cool thing. So we're gonna pick any 2 reals. Nice. We want Q, which is equal to the ratio of 2 whole numbers, such that, that m over n lives between those two numbers. There's some neat parts to this proof. There's some that's just like, I would have never thought of that. It's like, it's weird. So I might even have to look back down at my notes because there's a little subtlety on getting there, but I'm gonna try to not. Okay, so let's assume A and B are both positive numbers for the sake of this picture. So here's 0, and then here's A, and let's exaggerate a little bit. There's B. They don't have to sit like that. One could be, you know, they could straddle 0. They could both be negative, but the picture will get you the idea. So the first thing I'm going to do is figure out how long this is. So what is this width right here? That's B minus A. So that's the width of this. And I want to choose cut marks that are smaller than this width. So I'm going to choose n such that 1 over n is less than that distance. Thanks, Archimedes. Again, good old Archimedes coming through. This is truly primal stuff, right? So what we're going to do is we're going to take this width and pick a cut size that's smaller than it. So we're going to cut this thing up into 1 over n's. So this will be 1 over n, 2 over n. And right now I see this distance here. That's 1 over n. It's smaller than this. In this way, if I keep making these steps by 1 over n, eventually I'm going to land inside here. Something over n will land inside there. So if you can just make sure you believe that first. Does that sound reasonable? Let's think. And if there's any questions, let's talk about it.
Well, could you get it where it's like equal to A? And that wouldn't be a problem because you just add one more and then it's
Yeah, exactly. You could. You totally could, but you could still go smaller then, right? We definitely want that to be exclusively less than. So you're right, it could potentially be equal. You've picked too big. Shrink it.
Is that a box over n?
Yeah, that's a box,
Okay,
because
perfect.
that's gonna be what we need to find.
Okay.
We need to figure out which multiple of 1 over n falls inside there. And that's the thing we're gonna build, and once we do that, we literally, that box will be m, Kayla.
Okay, so I can't just decide to put n there?
You can't yet, no, I know, let's not yet, let's build it so that m is there, because it's not there yet. If we put it there, then we might think the proof is done and that we've done something.
Dang it.
Not yet. Not yet. We've done something, but not that yet. Okay, so let's check out this statement here. In order for, so first off, just like a little note to yourself, note, now we need m. So this is going to be the denominator of our fraction. And we're just going to find the first multiple that lands inside there. So in order for this to be true, we must have multiply through by n. I just flattened out the fractions, so now I've got some number. It's not necessarily a whole number or anything like that, but it's a number. So now I've got NA is out here, whatever that is. I'm going to appeal to Archimedes again and say, there's a whole number to the right. There's some whole number to the right of n times a, because otherwise the numbers stopped and they don't keep going, and that's a weird world that we don't live in. So we know that there's some whole number out here. What I'm going to do is choose the smallest one, the smallest whole number to the right of NA. And let me make sure I'm proceeding correctly. Yes. So let m be the smallest whole number, smallest integer, I guess we probably should say. Smallest integer.
Yeah, you want m to be a whole number, so you probably want m to be an integer.
Yeah, right, because otherwise we've kind of lost half our line. Yes, absolutely. So let m be the smallest integer, because that could be negative. No? Oh, wait.
What do you want?
I'm worried about being on the left now and using that word, right? Oh. As long as I put this will make a button. Oh, safe. Is that true? Is that what I want? And yeah, actually, let's make it, sorry, put it as strictly greater than, right there. There we go. Okay, so here's m. There's no whole numbers closer from this side. What does m minus 1 do? What is the relationship between m minus 1 and na? Where does it live in relative to na?
Less than or equal to?
Yeah, it must be over here, right? Because if it wasn't, I sure didn't pick the smallest one from this side. If m minus 1 is still here, why didn't I just pick that as m? So if this is the smallest whole number here, m minus 1 must fall to the left or possibly on na. Because we picked it strictly greater than. Thus, m minus 1 is less than or equal to na, and we're almost done. So this means that m is less than or equal to na plus 1. Now all the hard work is done and the beauty starts just unfolding. Look at how we already know. Well, hold on a second here. I want to try to get m to be less than nb over here so that I can divide through by n. So I need to get this related back to b. Let's take this thing and call it star right here. Since star says that a is less than b plus 1 over n. Do you believe that? Minus 1 over n. You see how I just took that thing and moved a to the left and moved the 1 over n to the right? There's nothing too fancy there. We know, multiply through here by na, so na is less than nb minus 1. So I just multiplied this statement by n. Times n. And now I can put that in, put this together and this together. And what I've got is what follows here. So we've got m less than, I'll write the whole thing up again, na plus 1, and that is strictly less than because na is bounded above by nb minus 1, that's this, plus 1. So m is less than strictly nb. Look what else we had. We know this also. Also, yeah? So put those two together, i.e. we've got na less than m less than nb, divide by n, and we're done. That's pretty crazy construction. So divide by n, and we've just produced our Q right here. It all seems so reasonable at doing it, but man, if you had to come up with this on your own, like it could take a while. take me a long, long while, personally. All right, friends, is there any questions on that? Because I wanted to work a few problems together out of this. This is consequences of 414. You don't need to remember this proof. I will never ask you this proof. You simply need to know what this means. That between any two real numbers, there's a rational. You're good to go. We've paid dearly for it. So, oh, here, fun.
I do have.
Yes, Noah.
So I remember from abstract algebra, there are the same amount of real numbers as there are integers by some proof. And
That's not quite true. That's not true, actually. But I know where you're thinking about.
yeah. Well, they're both countably infinite.
Well, the reals aren't.
Yeah, the reals.
The reals are uncountable.
Rationals.
There you go. There you go. Yes, sir.
So.
Yes. And we will get into that.
I'm just
Absolutely.
like. Sorry, I meant the rationals.
This is good. I'm glad you're like getting upset about this. This is great. It's worth being upset about.
So then the irrationals would have to be uncountably infinite.
Correct.
And so then there are more of them?
Mm-hmm. A lot more.
How do we show that?
We will show that. We will get to that. We're actually going to talk about cardinality and size because let me make sure everybody else knows what you're talking about because this is fun. Where the hell did my pen go?
I don't know why I was thinking of this now.
Well, because we're thinking about the rationals in your brain is starting to head to
yes.
infinity, and it should. And that's exciting. So the thing that Noah's alluding to is that there's different sizes of infinity. The simplest one means you can list everything. So you can literally just make a list. Like, you got it, you get it, you know what's next. You can figure that out. There's a pattern, and I can list them all. And if I told you 1,000's in that list, you believe me. And you should, because I intended to. So all the natural numbers are in this. We can also list the rational numbers. And that's crazy. And I don't want to get too deep into that, but I can list. So, I mean, and there's actually the same number of these as there are all integers, right? I could say, well, let's see here. 0, minus 1, 1, minus 2, 2, minus 3, 3. Right, so now you believe every integer's in that list. I would hope so. So there's the same number of integers as there are natural numbers, which seems crazy because one's doubly infinite and one's just infinite on one side. But there are also, we can list, there's a scheme for listing every rational number. And so the Q, the Google, whatever, this is the same size as that. There's actually as many rationals as there are. But man, do they sure act a lot different than these guys. They are clustered. Michael, yes, sir.
We're playing this game. I've read about them and I don't understand that much, but what is the cardinality then of the transcendentals? Or is that also
I don't
uncountably-
know. I don't know.
Okay.
I don't know what the so the transcendental numbers are any number that aren't solutions to an algebraic equation.
Integer coefficient polynomial.
Integer coefficient polynomial, yeah. I don't know if they're countable or not. That's a damn good question. I'm going to say countable, actually. I would think countable. I don't want to get too deep into why.
Okay.
Yeah.
So do we know like how much larger they are, or would that
Yes.
be? We do.
We do. Yeah.
Okay.
Yeah. I mean, so if you can't be listed, you are uncountable. And like I said, we will absolutely, you're going to be thrilled because we're going to get into this in detail. So down here you've got countably infinite. And that's, all these good friends of ours. That's down here. And then you jump up to uncountable. Uncountably infinite. I can't be listed. We'll prove that. We'll prove you can't list the real numbers. And by a quick little argument, you can't list the irrationals. But there's a thing called the continuum hypothesis. And the one thing we don't know, Noah, is if there's an infinity between these two.
Okay.
So the one thing, I think Cantor proposed this continuum hypothesis, that there could be one inside here, one between these two.
But not like an infinite amount of infinities, just one.
No, there's an infinite amount of infinities.
Well, no, not like an infinite amount
Yeah.
of infinities between them.
Yeah, at least one.
Okay.
It seems like once there's one, there might be, yeah, who
Yeah.
knows?
Well, it sounds like a thing where it might just be like, there are infinite infinities, so if you have one type of infinity, but in fact, we do the same proof that there's always an infinity between two infinities.
Absolutely, yeah, exactly. And yeah, there's definitely an infinite list going up this way of infinities, getting bigger and bigger, that are non-comparable. But the thing we do know is that if there's an infinity between these two, everything's okay, and if there isn't, everything's okay. That's all we know.
So, okay.
We do know math still is okay.
But we can't like quantify the amount more.
We have no idea. Yeah, no one has demonstrated that there can't be or produced an example of one that is.
Okay.
It's insane. It's truly insane.
So since we're talking about different sizes of infinity, like, I don't know if this makes sense or not,
Yeah.
but how can the naturals be the same infinity as the integers? Because the integers has 2 times plus 1.
Right.
The values that.
I saw that on your face. I
Yeah.
knew that's what you were thinking.
Uh-huh.
Because I can make a list of them, right? So this list is 1 to 1. For each one of these, there's an integer, right?
Okay.
So
Well,
there's a
2
1-to-1
integers.
correspondence.
There's a 1 to 2 correspondence, is there not?
Not the way I'm setting it. And even if there was.
Okay.
Do you see what I'm saying? So I'm like
Yes,
saying
I
1
do.
goes to 0, 2 goes to that. And then we could
Okay.
come up with a rule, which would probably be
Annoying.
challenging to
Yes.
come up with. But for each one of these natural numbers, there's one of these, and for each one of these, there's a natural number.
Okay.
So there's the same number, which is crazy.
All right.
Yeah. It's
Sounds
good
good.
stuff. It's the best. Coming soon to a real analysis class you know of. Quite soon. Fun. Thanks, Noah. Always happy, always happy. Let's dig into Q some more. We've got like 5 minutes. Let's take a look and improve our intuition about the rationals. Because they're good friends of ours. Okay, so this is exercise 141 in the text. And we're going to let I be the irrationals. And so here, I is the reals. Take out, that's set subtraction, the rationals. Everything that's left over once we pull out all the rational numbers. Show that if A and B are rational, then AB is rational and A plus B is also rational. Take a minute and convince yourself that this is true. And just an informal proof would be just fine. Be constructive. What does it mean to be in the rationals? It means you're something over something else. That's a good place to start with this proof.